Okay. So the statement, let me go back to the statement. So what was the statement? The statement says that if you have a finite group of some order and P is a prime number such that P divides the order of G, then it says that there is a subgroup of order P. Okay, this is what Cauchy's theorem says. So for that, what I have done, so I have considered this set, okay, such that this is the relation among the elements, okay, and I have considered, say, order of the group is n. Then what will be the cardinality of this set? We have observed each of them has n choices and the last one is fixed by this relation. Therefore, it will have n to the power p minus 1 choices. Now, P divides order of G, therefore P divides the cardinality of the set A. Okay. Then I have considered one uh, permutation, okay, of P cycle. Okay. So this H is a subgroup of this symmetric group with P elements, which is a P cycle. So order of H is nothing but P. Now I have defined this group action. Is this group action was clear?
Yes, ma'am.
Okay.
Yes, ma'am.
Now, what I was trying to say, I was trying to see what will be the cardinality of an orbit. Okay, so I have picked up any element S arbitrarily and then I am looking for what is the cardinality of the orbit. The theorem we have already proved, it is nothing but the index of the stabilizer. So this is nothing but order of H divided by order of Hs. So what was order of H? We have already seen it is P, right? So this is P divided by something. Then what are the, but P is a prime number. So then what will be the choices for the cardinality of the orbit?
1 and P.
Either it can be 1 or it can be P. Okay, whatever S element you choose, there are only two possibilities for the cardinality of the orbit. It is either 1 or it will be P. Okay, now we have already seen that every set can be written disjoint union as of its orbit because it gives you an equivalence relation. So I have written this set A as the disjoint union of its orbit. So orbit of S1 up to orbit of Sk. These are the disjoint union of the orbit. Now what is the cardinality of each orbit? Either they can be 1 or they can be P. Okay. Now, if I consider just the identity element, then what will be the cardinality of its orbit?
1.
1. So that means one of them, this S1, S2, Sk, whatever these are, one of the orbit will be the orbit of this identity element. Okay. So the cardinality of that set will be 1. Okay. So here say that this is the cardinality of this set is 1. Okay. Now, what is your cardinality of A? Cardinality of A was nothing but n to the power p minus 1. And p divides this. I have already seen. Okay. Now, suppose the cardinality of all these orbits are p. Then what I will get? That cardinality of A is nothing but 1 plus p plus p plus p plus p. Isn't it? Now, p divides this cardinality of A. So P should divide this side also. But 1 plus K minus 1 into P, is it divisible by P? So
No,
this
ma'am.
is
No.
1, this is P, this is P, this is P. Right. So what I am getting say 1 plus K minus 1 into P. So this should be divisible by P, isn't it? P divides this side. So P should divide this also, right? Are you following or not?
Yes,
Yes,
ma'am.
ma'am.
So P should divide this side also. But now 1 plus K minus, if all of them are of cardinality P, then I will get this side 1 plus K minus 1 into P, isn't it? But P doesn't divide this number.
Yes, ma'am.
So that means what it should be? That means not all of them has to be P. There will be some elements which are again give you 1. And how many of them will be there?
P times 1.
P times 1, right? So that means that is what I have written. So there must be at least P minus 1 elements in A such that the cardinality of the orbit is 1 apart from identity. Okay, but if the cardinality of the orbit is 1, then what we have seen? Then we have seen that element will satisfy this condition. Okay. Therefore, there exists at least P minus 1 many elements such that order of xp is equal to 1. Is this clear? If not, then which part is not clear? Is it still not clear?
Yes, ma'am, clear.
Clear? Everybody, it is clear?
Yes.
Yes, ma'am.
Okay, good. Okay, so now I will be considering some special cases of group action. Okay, so before that, let me just first, we have done Cauchy's theorem. Now we will do Cayley's theorem. So what does Cayley's theorem says? It says that every finite group G is isomorphic to a subgroup of a permutation group. And in fact, it says that if G has order n, then it is isomorphic to a subgroup of the symmetric group Sn. Okay, so that means in some sense with this theorem it is enough to study the symmetric groups, because it says that every finite group of order n is a isomorphic to a subgroup of Sn. So it is enough to study the symmetric group, because if you understand the structure of the symmetric group and all its subgroups, then you can in fact understand all the groups by this isomorphism. So now let us try to prove this theorem. So again we will prove this by group action only. So I will consider the group action by left multiplication. So consider the group action G cross G to G defined by G cross X is going to Gx. This is by left multiplication. So this is what? This is nothing but the operation of the group. Okay. So this group action is nothing but the operation of the group. Okay. So now this will define a group. So now I would like to show that this is isomorphic to a subgroup of the permutation group. But how do I, from a group, how do I go to the permutation group? Any guess? From a group, how can I go to a permutation group using some group action? Any idea? Yesterday I have
Permutation representation
yes, yes,
group
yes,
action.
correct. Yesterday I have defined the permutation representation of a group action. So what does it did? So the permutation representation of a group action define a group homomorphism from the group to the symmetric group, isn't it? So now using the permutation representation of a group action, we define a group homomorphism, say psi, from the group G to S. So what was this, in which group we have defined this, if the group was of like we have defined it in the symmetric group with n elements, if this is of order n. Okay, how did I done this thing? So we have considered any element of the group and we have sent it to sigma g. What is sigma g? Sigma g was a map from the set G to G. How we have defined this map? So sigma G of any element of the set X, I am sending it to Gx. Is it okay?
Yes, ma'am.
Yeah. So corresponding to each G, I have got a sigma G, where this sigma G is a map from the set G to G defined as follows. Okay. Then I'm not checking this. I think I have given you an exercise. This psi is a group homomorphism. This is true for any general group or any general set. Nothing too special about this particular group action. So this psi is a group homomorphism. Psi is a group homomorphism. And what is the kernel of psi? Have not checked it, then check it right now. What is the kernel? Kernel is all the elements of the group G such that sigma G will be the identity map, isn't it? What does that mean? That sigma G is the identity map? That means sigma G of X should be equal to X for all X belongs to G. Correct? What does that mean? That means this is all the elements of the group such that Gx equal to X for all X belongs to G. What will be the kernel?
Identity element.
Only identity element. Therefore, what I am getting? I am getting that G is, so this is an injective group homomorphism. So therefore, G is isomorphic to its image in SG. So that is, if order of G is n, then G is isomorphic to a subgroup of order n of Sn. Okay. Is it okay?
Yes, ma'am.
Okay, fine. Now, next thing what I will do, I will consider now the group action by conjugation. So now, basically what we are doing, and so once we have learned this group action, and after that we are taking different types of group action and we are proving theorems. For example, Cauchy's theorem, we considered a particular type of group action and proved Cauchy's theorem. Galley's theorem also, we have considered the group action by left multiplication and we have proved Galley's theorem. So group action is in fact a very useful tool. Okay. But in order to apply that, you need to have an intuition of what type of group action you should choose so that you will get the desired result. Okay, so now I will talk about the group action by conjugation. So group action by conjugation. What is the group action by conjugation? So I think I have already defined this. So let me just brief quickly. So let G be a group. Then and consider A to be equal to G itself. That means the set also I am considering the group itself. Okay. Then we define the group action by conjugation as follows. So it will be a map from G cross G to G. So take any element from the group G and take an element from the set G, that is X, and I'm sending it to Gx G inverse. Okay, you can check that this is a group action. Okay, it is not difficult. So is it clear what is the group action I'm considering? So this is basically Gx G inverse is nothing but the operation in the group G. Okay, because we have already one binary operation defined on G, and with respect to that operation I am considering Gx G inverse. So it will again be an element of the group G. So the operation is the group operation. Okay, now what will be the stabilizer of an element here? What was the definition for stabilizer? All those elements of the group such that it fixes the element of the set, right? That means Gx G inverse should be equal to X, isn't it? So this is, yeah, this is the collection of all the elements of the group such that Gx is equal to Xg. That means this is nothing but I'm considering all the elements of the group which are commuting with that particular element X. Correct? This says that all the collections of G such that it is commuting with this particular element X. X is fixed. Okay. So this has a special name when I consider this group operation by conjugation, then this stabilizer is called the centralizer of X. And and it is denoted by CX. So this is just another notation to denote the stabilizer for this particular group action by conjugation. So this is then called centralizer of X and it is denoted by CX. Okay. And what is the orbit? Orbit is nothing but Gx G inverse such that G is varying over all the elements of the group. So this has also a special name. This is known as the conjugacy class of X. And it is also denoted by CX. Okay. So please remember these two terms. These are very useful. Now we will learn how to find the conjugacy class of a group. In that way, these two terms will be useful. So for this particular type of group action, which is the conjugation, for that the stabilizer is known as the centralizer and is denoted by CX, and the orbit is known as the conjugacy class, which is denoted by C suffix X. Okay. Is this fine? So now what do we know? We know that the orbits give you a partition of the set, right? So here the set is the group itself. That means the conjugacy classes give you a partition of the group. Okay. So since,
Hello, ma'am.
yes.
Ma'am, the centralizer and conjugacy class of X. If we not define that this conjugate group action, then is there any way to say that this is centralizer or this is conjugacy?
No, this is the special name for this group action. This is in terms of group action, this is nothing but the stabilizer and orbit, right? But whenever we are considering this particular group action, which is by conjugation, for this particular group action, this stabilizer is known as the centralizer and the orbit is known as the conjugacy class. This is only for this particular group action, not for any other.
Okay.
Okay. Yeah. Okay. Now, since the conjugacy classes are orbits, so they partition the group G. Okay. Now, let's go back and see what does it mean by having only one element in the conjugacy class. So suppose this orbit is having only one element. What does that mean? The cardinality of the orbit is 1. What does it mean?
It means group in characterize one element on.
No, I'm saying that if this orbit of X is just having only one element, okay, so then what does it mean?
It contains only identity.
So conjugacy class is of size 1. That means, so X is there in the conjugacy class, right?
And then X
Yes, ma'am.
commutes every element.
Yes, correct.
group might
Then
be-
X will commute with all the elements of the group G, right? That means X will be in the center of the group. So let me write down. Note that an element X belongs to G have conjugacy class of size 1. Then it implies that, what does it imply? That implies that Gx G inverse will be equal to X for all G belongs to G. Because X will be in that orbit of X, no?
Yes,
So
ma'am.
that means what? That means Gx is equal to Xg for all G belongs to the group. That implies that X is in the center of the group. And in fact, this is an if and only condition. That means if I start with an element which is in the center, that means that Gx will be equal to Xg for all G. That means that in that case, the conjugacy class will be of size 1. Isn't it? So that therefore, an element X belongs to G have conjugacy class 1, class of size 1, if and only if X is in the center of the group. Okay, so that means if an element is in the center, then its conjugacy class will be of size 1, and conversely, if a element if the conjugacy class size is 1, in that case that element has to be in the center. Is it fine? Are you able to follow?
Yes, ma'am.
If you are not able to follow, then please tell me. Otherwise, I will assume that you are following and I will go on. And it will not be useful at all. So, now I am going to define the class equation. So, in order to do that, so let G be a group of finite order and the center of G. Everybody remembers what was the center?
Yes, ma'am.
Commuting element.
Yeah, those elements which are commuting with all the elements of the group. That was the center. Okay. So now I am having a finite group G. Okay, and its center, I'm saying, say it has these many elements. Of course, identity will be in the center. And suppose there are Z1, Z2, Zm are the elements which are in the center. And let CG1, CGR be the conjugacy classes of G, be the conjugacy classes of G not contained in the center. That means, what does that mean? That means this G1, G2, GR, these are not elements of the center. Okay, because if these are elements of the center, then its conjugacy class will be of size 1. So I am writing all the elements of the all the elements of the center separately, and for those elements which are not in the center, for them I have find out these are the only distinct conjugacy classes. Okay, and now what do we know? I know that the set of all conjugacy classes partition G, right? Since G is a partition of all conjugacy classes, what we are having, so I can write down my G as disjoint union of the conjugacy classes. So one conjugacy class will be corresponding to identity, then there will be corresponding to the elements of the center, and then there will be the others one. Is it clear? Because for each element in the center, I will get a conjugacy class of size 1. So now you observe that all of these are
Ma'am,
of
please.
size 1. Yes.
Ma'am, please explain once again last.
Okay, so I'm saying that G is a partition of all its conjugacy classes. This line is clear?
No, ma'am.
Okay. So what are the conjugacy classes? Conjugacy class are nothing but the orbits.
Yes, ma'am.
And what do you know about orbit? That orbit gives you a partition of the set.
Yes, ma'am.
So now here the set is the group G. So G can be written as disjoint union of the orbits,
Yes, ma'am.
which are nothing but the conjugacy classes.
Yes, ma'am.
So that's why here I have written G as disjoint union of the conjugacy classes.
Ma'am, here one Z1, Zm, after that G1, G2, Gn.
Yes. So here what I have said, okay, that the center has this many elements. Okay. So apart from the elements of the center, I am saying that the remaining whatever elements, they are in the following conjugacy classes, CG1 and CGR.
Okay,
So
ma'am.
G1, G2, GR are the elements which are outside the center, and their conjugacy classes is filling out the whole of the G. What we have observed that for elements of the center, the conjugacy class is of size 1. This line.
Yes, ma'am.
Okay. So I have separated those elements now and the remaining elements. So here I have written this thus G as disjoint union of these elements. So these are the conjugacy classes of size 1 because these are elements of the center. Okay.
Yes, ma'am.
So now cardinality of G is nothing but 1 plus 1 plus 1 plus cardinality of the conjugacy classes. So this is nothing but cardinality of the center plus cardinality of the other conjugacy classes. So this is known as the class equation. Is it okay?
Yes, ma'am. Can you give some example?
Yes, I will give examples. first let me give you some applications of this, and then we will explicitly compute the conjugacy classes for some groups. Okay. So far, is it clear to everybody?
Yes,
ma'am.
Okay. So, as somebody already asked for the example, let me just first go to the example first. Let group G is S3. Okay. Write down the class equation. Of S3. So if you want to write down the class equation for S3, then what you have to do, you have to pick up one element, and for those elements you have to find out what are the conjugacy classes, right? Fine. So first let us see what is the center of S3. What is the center of S3?
identity element.
Identity element, right? So note that the center of S3 is only the identity permutation. Okay. So here the cardinality of the center is 1. Okay. So corresponding to this term, I will just get 1. Correct. Now I need to find out the remaining. Okay. So now you start with a 2 cycle. So let G1 is this 2 cycle. Okay. Then what will be the conjugacy class for G1?
G1 G inverse.
Yeah. So the conjugacy class is nothing but the elements of the form sigma 1 to sigma inverse, such that sigma is varying over all the elements of S3. Isn't it? Now can you explicitly tell me what will be the elements here?
1, 2, 2, 3, and 3, 1.
This will be 1, 2, 2, 3 and 1, 3. 3 elements, isn't it? Now what will be the conjugacy class of 2, 3?
Ma'am, how we find in very few time?
It is, I will tell you, explain it once again, but what I have told in one of the exercises, I gave you what will be this, how to write this one.
First, yes,
Isn't
ma'am.
it?
First question of tutorial 2.
Yeah. So I have applied this thing only.
Yes.
This expression. Applying that, you can find it easily. In fact, all the cycles of same types will be in the same conjugacy class.
Okay, ma'am.
Okay. So in fact, if I choose my G2 to be equal to say 2, 3, then what will be the conjugacy class for G2? It will
Same
be
as G.
same as the conjugacy
G1.
class of G1. Okay. So all the 2 cycles are in the same conjugacy class. Okay. Now what about the conjugacy class of this element, G3?
1, 3, 2 and 1, 2, 3.
Yes. Sigma is over S3. So this is nothing but the elements will be 1, 2, 3 and 1, 3, 2. There are only 2, 3 cycles, right? So therefore the class equation will be what? In fact, similarly, this will be the conjugacy class of, if G4 you choose to be 1, 3, 2, this is same as the conjugacy class of G4. Check. Okay. Therefore the class equation of S3 is 3 equal to 1 plus 3 plus 2.
From 6 equals to.
Oh, sorry, 6 equals to. Yeah, sorry, 6. Now is it fine?
Yes, ma'am.
Okay. Now I will give you a general exercise. This is also in the tutorial sheet also. Next tutorial sheet we will discuss in the tutorial class. But in general, maybe I will just, for the exercise, I will ask you to describe the conjugacy class of S4. And then you try to generalize it for general N, Sn, which will be have many choices. Okay, fine. So this I have given you one example of class equation. Now let us see some beautiful applications of this class equation or this conjugacy classes kind of thing.
Isn't there a short way, like if the order of the group is keep on increasing, then the complexity will increase in this?
Yes, definitely. Definitely.
There isn't a shorter way for doing this.
It depends on the group structure. When you do it for Sn, then you will see that it is not that much difficult, because you know that all the same cycle types are in the same conjugacy class. Then you just need to find out the how many elements are there of a particular cycle type. That will give you. But apart from that, it is not that much easy.
Okay.
Okay. So some applications. So before giving you the application, let me define one thing. So a group of order p to the power n, where p is a prime number and n is a natural number, is called a p group. Okay, so a group of order p to the power n is called a p group. So now we will, using this class equation, we will derive some nice properties of the p group first. Okay. The first one. Sorry.
Ma'am, please show the previous slide.
Yeah.
Okay, ma'am.
Okay. So let G be a P group. Then what can you say about the cardinality of the center of G? Then it says that it will always be greater than equal to P. Okay. That means if you have a P group, then its center is always non-trivial. Okay. That means it says something stronger also, because you already know that the center is a subgroup, and not only that, it is a normal subgroup also, right? So that means it says that if you have a P group, then it has a normal subgroup, non-trivial normal subgroup. Okay. Okay, so let us try to prove this thing. So suppose that the center is trivial. What does it mean? If the center is trivial, then from the class equation, what can I say? That order of G is equal to, what was the class equation? Order of the center, cardinality of the center, plus summation of the conjugacy classes. Okay, isn't it? Now, what does it say? This says that this is order of G, this is 1 plus this summation. Now, what is the cardinality of this conjugacy classes? What can you say about the cardinality of the conjugacy classes?
Order group upon normalizer order.
Yeah, so what are the choices for that? Given that G is a P group.
Some p to the power type.
P to the power something, right? So this is nothing but the index of the stabilizer, right? So this is nothing but G colon CGI. Okay, so this is nothing but order of G divided by order of the centralizer, right? But what is order of G? Order of G is P to the power, say some M. Okay, so that means what will be the choices for this? This will be P to the power something. That means it is divisible by P. Okay, so now is it possible? Look
No,
at this equation. Each of them is divisible by P, and you have 1 plus some multiple of P, and this is also divisible by P. Is it possible? It is not, right?
no, ma'am.
So that means this one that I have assumed, it is not possible. Okay. So since P divides order of G and P divides all of these conjugacy classes, we get a contradiction from equation 1. Therefore, the cardinality of this should be greater than equal to P. But why it will be greater than equal to P?
Since it divides order of group, so it can be at
Yes.
least P.
Yes, correct. Because this center is a subgroup. Okay, if it is non-trivial, then its order should divide the order of the group, and the order of the group is P to the power something. So it would have to be at least P. Okay, good. Now the next application. Should I go to the next page? You are done?
Yes, ma'am.
Okay. So as a corollary to this, the above one, we can say that any group of order P square is abelian. Okay, any group of order P square is abelian. That is what we will prove next. So what we have already known that this is a P group, order is P square. So the center is non-trivial, right? So by the previous proposition, we have that the cardinality of the center is greater than equal to P, isn't it? So now there are two choices for the order of the center. What are the two choices?
P and P square.
Either P or P
Either P or
square.
P.
Either P or P square. So now if the cardinality of the center is equal to P square, then what will happen?
We are done. It is
We are
already
done.
P.
Yes.
Because
Away.
in that case ZG is equal to G, thus G is abelian. So we are left with the case that if the cardinality of the order of the center is P, then what will happen? So let the cardinality of the center is equal to P. If its order is P, that means there are elements which are outside the center. So let X be an element of the group which is outside the center. Okay. So then what can you say about this what can you say about the centralizer of X? What can you say about the centralizer of X?
Order of centralizer of X will be P.
Will be P?
Yes, ma'am.
But why it will be P?
Since we have only two choices, P and P square, and if it will be P square, then X must be belong to center of Z.
Yeah, so basically what we are having, but we have C in the centralizer X is also there, no?
Yes, ma'am.
So note that this center of G is strictly sitting inside the centralizer of X, isn't it? Is the center is of the group sitting inside the centralizer of X or not?
Yes, ma'am.
Yes, because center is the collection of all elements which commutes with all the elements of the group. So certainly it commutes with X also, right? It is the collection of all the elements which commutes with all the elements of the group. So therefore, or it commutes with particular X also, right? So that means the center is sitting inside the centralizer of X, isn't it?
Yes, ma'am.
Yes,
So
ma'am.
that means what? That means the centralizer is, and also I have this X which is in the centralizer but not in the center. That means what? That means this centralizer is strictly bigger than the center. Isn't it? Here I have proved that center is sitting inside the centralizer and I have one element which is only in the centralizer but not in the center. Okay. That means then what will be the cardinality Cx centralizer? It has to be equal to P square
Yes, ma'am.
because there are only two
Yes.
choices, right? So, but if this is equal to P square, then what does it say?
That the
Which will be a contradiction, right?
Yes, ma'am. Since S, because it happens, then X belongs to center of Z.
This is not possible.
Yes.
Ma'am,
So
centralizer
which
is
is a
also,
contradiction.
ma'am, centralizer is also
Sorry.
a sub. What?
Yes, that you can prove. Okay. So which is a contradiction. Therefore, so the contradiction arrived because I have chosen that cardinality of the center is equal to P. That means this should not happen. That means I should have that the center of G should be equal to G. Hence, G is abelian. Is it fine?
Hello, ma'am.
Yes.
Mm. Ma'am, order of centralizer X equal to P square. From which this implies.
See, this centralizer is also a subgroup. This
Yes, ma'am.
centralizer is also a subgroup. Now I have assumed that order of the center is P. Okay. And centralizer is strictly bigger. That means its order should be strictly greater than P. Okay. But what is the order of the group? Order of the group is P square. So since the centralizer is a divisor, the order of this will be a divisor of the group. So therefore it has to be equal to P square. Because for P square, what are the possible divisors? 1, P and P square.
Okay,
And
ma'am.
it has to be strictly bigger than P. So therefore it has to be equal to P square. Is this fine?
Yes, ma'am. I thought that there will be another reason for that. Okay.
No, only this one. Okay. So now I will do one more corollary and then I will give you break. This is just in the continuation. So I would like to, yes.
Ma'am, can you once again explain the contradiction, why it is there?
Why it is a contradiction? So what does it mean? Um, did you understand that this is equal to P square?
Yes, ma'am.
Okay. So now that means the centralizer is the whole group. From this, it implies that Cx is the whole group. What does this mean? That means X is commuting with all the elements of the group.
Okay, ma'am, got it.
That will say that X belongs to the center. But I have chosen my X to be outside the center. Okay?
Yes, ma'am.
Okay, fine. So now, just another corollary. Any group of order P square is isomorphic to either Z quotient P square Z or Z quotient PZ cross Z quotient PZ. Okay. So it is saying that any group of order P square will be either a cyclic group of order P square or it will be this. This is not a cyclic group. This is the product of two cyclic groups. Okay. So these are the only two choices if you have a group of order P square. So let us try to give you a proof of this fact. We already know that any group of order P square is abelian. Okay. So let us consider any X which is a non-identity element belongs to G. Okay. Then what will be the order of X? If I want to prove that this is a cyclic group, then that means there should exist an element of order P square. That is what I have to prove if I want to show this is isomorphic with this. Okay. So now what will be the choices for order of X if X is a non-identity element? Order of X will be equal to
P or P square.
P or P square. Okay. Now if order of X is equal to P square, then What I
then
can say?
X will be the generator of the group.
Yes, then in that case, G will be isomorphic with Z quotient P square Z. Correct? Because order of X is P square. That means the group G is generated by X. That means G is nothing but the cyclic group of order P square. Fine? This statement is clear?
Yes, ma'am.
Okay. So now I am assuming that, so that means if there exists one element of order P square, then this group will be isomorphic with this one. We don't have to do anything. Okay. Now assume that there does not exist any element of order P square. So let there doesn't exist any element of order P square. Okay. And X is a non-identity element in G such that order of X has to be equal to P, right? If you consider any element now, okay, in the group which is a non-identity element, then its order has to be equal to P, because I am assuming that there does not exist any element of order P square. So all the elements, non-identity elements of the group have order P, correct? Is this fine?
Yes, ma'am.
Now I'm considering H to be the cyclic group generated by this X, and I'm considering one element Y which doesn't belongs to H. Okay. Then what will be the order of Y?
P.
P only, because I don't have any other choice. Okay. Now let K be the subgroup which is generated by Y. Okay. What can we say about H intersection K?
Only identity.
Only identity, because H intersection K is a subgroup of H as well as it is a subgroup of K. So its order will be either 1 or P, but this Y I have chosen which is outside H. That means it cannot be equal to one of them. So it has to be equal to identity element. Okay. Now I already know that since G is of order P square, thus G is abelian. So since G is abelian, what I can say? That H and K both are normal subgroups. Okay. So then HK will also be a subgroup of G.
Yes, ma'am.
Then HK is a subgroup. Yes, just let me finish this. The subgroup of G which is strictly bigger than H. Therefore, order of HK is nothing but P square. Hence, I am having G is equal to HK. Therefore, G is in fact isomorphic with H cross K, which is isomorphic with Z quotient PZ cross Z quotient PZ. Is it fine? So I have when I think last week I have done this when I can write a group as a product of its two subgroups. I have there given you the criteria under which conditions we can do that. So if both H and K are normal subgroups, in that case if G is equal to HK, we can write down in this way. So I have applied that theorem only here. Okay. So now previous slide.
Ma'am, here G is abelian and S and K both are known. How G is abelian?
Last corollary, what we have proved? What we have proved in the last corollary, previous corollary? Any group
Yes.
of order P square is abelian. So therefore G is abelian.
Okay.
Okay. Whatever I am using now, I will be used more frequently all these facts. So read it carefully and remember these facts. Otherwise, you will not be able to follow. Okay. You have to give more time now. Fine.
Yes, ma'am.
Okay, so now we will have say 10 minutes break and then we will meet again. So it is we will meet at 10:20. Now it is 10:12 in my clock, so we will meet at 10:20 and we will discuss the tutorial sheet. Okay? Fine?
Okay.
Okay.
Okay.